pleasure to it's my pleasure to introduce Kriti Goel from University of Utah, and she will speak on the Hilbert-Kunz function and Hilbert-Kunz multiplicity of ideals and Riesz algebras. She will talk for about 40 minutes, and we'll have a break, and then she'll talk some more, and we'll have some questions at the end.
Thank you. Thank you, firstly, the organizers for inviting me to give this talk today. It's a real honor speaking today in the Fellowship of the Ring seminar series. So, of course, I'll be talking about these functions, Hilbert-Kunz functions and Hilbert-Kunz multiplicity. We'll be talking about two things today. We'll be talking about the setup in the case of Riesz algebras, and the second part will be about looking at powers of ideals and their Hilbert-Kunz functions and multiplicities. This is kind of a culmination of three papers of mine, three recent papers of mine, which are kind of joint works with Arindam Banerjee, Mitra Kole, and Professor Jugal Verma. So I guess I'll just start with a quick setup. And of course, since the setup requires characteristic P, because the Hilbert-Kunz function and multiplicity are defined in characteristic P, I'll firstly assume a general setup because I want to recall quickly a classical notion of Hilbert-Samuel functions and multiplicities, and then we'll shift to the characteristic P setup and proceed. So the setup is as follows. For us, R will always be an Noetherian ring. Mostly I prefer it to be local as well. Wherever I do not need it to be local, I'll mention that. And of course, it's a commutative ring, it has unity. Then M will be the maximal ideal of this local ring. D will always be the Krull dimension of the ring R. And I, wherever J comes, these are all ideals. So that's broadly the set of notations that I'll be using. So as I mentioned, I'm not assuming characteristic P as of now to begin with. Why? Because I want to introduce something, or rather recall something, which is called as Hilbert-Samuel functions and Hilbert-Samuel multiplicities. So what are really those? So let's first define what is a Hilbert-Samuel function. So if you have an ideal I, which is M primary, so just quickly, what do we mean by an M primary ideal? This is an ideal I such that length of R over I is finite. So once you have this, one can look at length of R over I to the n for any natural power or the ordinary power of the ideal. And this is what is called as the Hilbert-Samuel function of an ideal I. I'm kind of suppressing R over here because for me, I'm just talking about the ring R. We're not going into the modulo case. So we'll just denote this by h sub I of n. And this is what is called as the Hilbert-Samuel function. And one nice property that this function has, and it is so extensively studied for, is that h sub I n is a polynomial function. So what do we precisely mean by that? This means there exists a polynomial. Let's denote this by p sub I of x, such that a few things happen. First of all, when we look at the Hilbert-Samuel function, this coincides with the Hilbert-Samuel polynomial. This is what we'll start calling it as for all large values of n. What are the other things that we know about this polynomial? Degree of this polynomial, p sub I of x is equal to d, which is the Krull dimension of the ring, and the coefficients of this polynomial are rational. Okay, what else? It's a polynomial, so this means you would like to write it nicely, and the preferred way is to write it as linear combination of binomials. So one preferred way of writing this polynomial is as follows. You'll have certain coefficients followed by certain binomials. So this is x plus p minus 1, choose p. P again is a full dimension. Then again, another coefficient, e1 of I, x plus p minus 2, choose p minus 1. And this will further keep on alternating until we have the last constant term. And these are just not any random coefficients over here that we are talking about. These are special coefficients, and these are what are called as the Hilbert-Samuel coefficients of an ideal. So E sub I of I, these are what are called as the Hilbert-Samuel coefficients of I. And of course, since I just precisely did not write, EIX is what we call as the Hilbert-Samuel polynomial of I with respect to the ring. But in all these Hilbert-Samuel coefficients, the one very interesting one and very extensively studied one is the leading coefficient, which is E sub 0 of I. It's extensively studied by geometers and is called as the Hilbert-Samuel multiplicity of the I. Of course, the other way of writing it or defining it is looking at this number as the asymptotic limit of the Hilbert function over n to the d, but we also have a normalizing factor, which is e factor. And that's how we define the Hilbert-Samuel multiplicity of an ideal. So a few things to note here. When we defined the Hilbert-Samuel function, it was a polynomial function. And when we looked at the Hilbert-Samuel multiplicity, this is the asymptotic limit of the Hilbert-Samuel function followed by a normalizing factor. The other important thing about this, of course, there are many, but just something that I would like to point out over here is that it's an integer, or rather it's a positive integer. So that was just the recalling part of it. But now let's define Hilbert-Kunz functions and multiplicities and see how they differ or are similar with what we have already defined. So this means we now move to the characteristic we set up. So characteristic of the ring R is P and P is prime. So that's what we'll have until the end of the talk. So once we are in the setup, so the idea of defining the Hilbert-Samuel functions was to look at O-length of powers of ideals, ordinary powers of ideals. In characteristic P, can we replace the ordinary power with something else? And the idea over here is the following. In characteristic P setup, we have this Frobenius map from ring to itself, and it takes an element X to its eighth one. So under this map, we actually define what is called as the Frobenius power of an ideal I. So I guess let me just set up this notation as well. For me, Q will be a prime power, where E is a natural number. So let's fix this. And once we have this, we'll denote the Frobenius power of an ideal by I square bracket Q. This is the ideal generated by the qth powers of the elements of the ideal. Now, once we have this, and let's say we have the ideal to be M prime D, then the question is, can we look at length of R over I square bracket Q, and is this function interesting enough? And this function was actually started by Ernst Kunz in 1969, where he used this function to characterize regular local rings. And this is what we call as the Hilbert-Kunz function of the ideal. So now once you have this function defined, one would want to ask two questions, as we saw before. So first of all, is this function a polynomial function? Next question, does the asymptotic limit of this function exist? So let's look at the second question first, because this was answered by Paul Wronski in 1983, where he proved that if we look at the asymptotic limit to infinity of the Hilbert-Kunz function, Q to the D, where D is the dimension of the ring, then this limit exists. Let's denote this by E sub hk of I. And this is what we call as the Hilbert-Kunz function, or Hilbert-Kunz multiplicity of the ideal. So now we have a definition of Hilbert-Kunz function. We have the definition of Hilbert-Kunz multiplicity of the ideal. But how different or similar is this with the classical notion of Hilbert-Simon functions and Hilbert-Simon multiplicities? So first of all, I guess I'll just point out the differences over here. And one major difference is that the Hilbert-Kunz function need not be a polynomial function. And this was actually one motivation or one direction in this was given by Monsky in the same paper, where he looked at the nicest class of rings possible, nicest in the sense the lowest dimension, dimension 1. Of course, dimension 0 will not be that interesting over here. So let's look at rings which have dimension 1. And even in this scenario, Monsky proved that Hilbert-Kunz functions need not be a polynomial function. So that's the level of unpredictable behavior that one can expect, that one can see from Hilbert-Kunz functions. And that's what Monsky proved. Of course, the base assumptions are the same. Ring is a Noetherian local ring, characteristic P, but now we'll be having dimension to be 1. In this case, when we look at length of R over I square bracket Q, then so we at least know that this this function, Hilbert-Kunz function, will be linear in Q. In particular, of course, as expected, the leading coefficient is the Hilbert-Kunz multiplicity. It's linear, so that's multiplied by Q. But then over here, one would expect a constant to appear. What happens actually is that a constant does appear, but this delta sub E is actually a periodic function. In E for large E. So just to give you a quick example of what really happens, again, this example is from the same paper. We looked at the ring R, which is a quotient of power series ring, kxy over x to the 5 minus y to the 5. Of course, K is a field and characteristic is P, which is equivalent to plus minus 2 mod 5. So in this setup, Monsky actually proved that if we look at length of R over, so I'm looking at Hilbert-Kunz function of the maximal ideal over here. Then the Hilbert-Kunz multiplicity is 5 times Q. But then how does the so-called constant term appear? This is equal to minus 4 when E is even, and it is equal to minus 6 when E is odd.
So your E is Q to the PE. That's how you are defining E?
Yes, yeah.
Okay.
Yeah, that's true. Yeah, over here. I don't want to keep writing P to the E. That may just turn out to be a little more cumbersome. So yeah, my apologies for that. So that's my notation, Q is P to B. Okay, so at least we now know that the Hilbert-Kunz function need not be a polynomial function, and we have a correct result in dimension 1 and also an example to say what is really happening. And since we have the setup, let me quickly define what are called as quasi-polynomials, because this is something I'll be using later in my talk extensively. So what are quasi-polynomials? So let's say we have a function f from we can have it from set to C. Let's so function from set to C. This is called a quasi-polynomial. If two things happen, if there exists an integer capital N bigger than 0, and we have a bunch of polynomials, say G1 rather G0 up to Gn minus 1, such that when I'm looking at f evaluated at some number n, this will be G sub I of n if n is equivalent to I mod f. So it's basically, if you're writing this function in terms of the polynomial, a polynomial in n, then whatever appears as the coefficient of various powers of n. These coefficients themselves are periodic functions of n, roughly, but that's how I like to remember it, that it is equivalent to different polynomials depending on which point you're evaluating them at. So in particular, whatever we saw over here in the case of dimension 1, Hilbert-Kunz function is actually a quasi-polynomial function. Okay, so now once we have this, we have some idea about the Hilbert-Kunz function. Let's look at Hilbert-Kunz multiplicity. So we saw over here that Hilbert-Samuel multiplicity was an integer. But with the Hilbert-Kunz multiplicity, it is known that in several cases it's a rational number, but actually there are many other cases where it is still, where people are still figuring it out. That's one thing. But there are certain cases, of course, these papers are not yet published, they're just on archive yet, but we have some cases where it's speculated to be irrational. So I'll just mention one of those results. So this is by Brenner in 2013, where he proved that there exists a three-dimensional local domain M such that if we are looking at Hilbert-Kunz multiplicity of the maximal ideal, this is irrational. So that's how much they can differ. So this was just an idea, a setup of what these functions and these multiplicities are. But now let's talk about what we really want to do with them. So there is some literature where people have looked at various classes of rings and classes of ideals, and they have computed the Hilbert-Kunz functions and multiplicities. Of course, it's a computationally intensive task because it requires checking a lot many things. And of course, Frobenius powers are not very easy to work around with. Our idea was to look at ideals over Riesz algebras. So there are certain blow-up algebras called as Riesz algebras and associated graded rings. And we wanted to look at the Hilbert-Kunz multiplicities of ideals over these blow-up algebras. And of course, by the time we started working on it, there was only one paper which kind of gave certain bounds on the Hilbert-Kunz multiplicities of ideals of Riesz algebras. And of course, it was also in a particular setup. And that this is what we had to work on with. So I'll quickly say what those results were, and then I'll proceed towards what we actually did. So first of all, let me quickly define what is a Riesz algebra. Let's do that. So Riesz algebra of an ideal I, we need to know this by Ri. And this is, I'm looking at just the ordinary Riesz algebra, not the extended Riesz algebra. So for me, this is an n-graded ring whose nth graded component is I to the n to the n. And of course, the other graded ring is the associated graded ring of an ideal. And we denote this by G of I. Again, this is an n-graded ring whose nth graded component is I to the n over I to the n plus 1. So this is just setting up the notations, and let me quickly give you the result which we had from the paper of Ito and Yoshida. This is a paper in 2003. So the setup is again the same. We have another in local ring. We have an imprimary ideal I, and these guys prove that if you look at the Hilbert-Kunz multiplicity of the ideal, so if I say Riesz algebra of I, I'm over here referring to the Hilbert-Kunz multiplicity of the maximal homogeneous ideal. In particular, this is Hilbert-Kunz multiplicity of the ideal M, comma, plus in R. So if I just say Hilbert-Kunz multiplicity of the ring, this means I'm referring to the maximal homogeneous ideal. And over here, they prove that it's upper bounded by a constant, which is C times D times the Hilbert-Samuel multiplicity of the ideal. So of course, first of all, what is this number? This constant C time C of D is a fraction D times 1 over 2 plus 1 over D plus 1 factorial. So they just not gave a upper bound. They also said that moreover, if we have the Hilbert's multiplicity of the ring to be same as the Hilbert-Sample multiplicity of the ideal, then equality holds. And if I'm not wrong, this is actually an if and only if statement. So that's the result, the only result that was known about Rees algebras, and it was more so in terms of a bound, which is coming from a constant CD, and it is dependent on the Hilbert-Sample multiplicity of the ideal, which is, at least to me, was surprising to begin with, because we have Hilbert's multiplicity of maximal homogeneous ideal of the Rees algebra, and a bound connects it to the Hilbert-Sample multiplicities. So that's of course interesting in some sense. So this is what we had to work with, and our idea was to look at specific classes of rings, of course, start with dimension 1, and see if we can explicitly compute what is the Hilbert-Kunz function, Hilbert-Kunz multiplicity, and does it continue to be dependent on the Hilbert-Sample coefficients? Do they still appear if we look at the entire Hilbert-Kunz function? So before I give the results, let me quickly recall what is mean by a reduction of an ideal. I'll briefly require it at some parts. So let me just quickly do that. Okay, so for this, we do not need ring to be local. You can define a reduction of an ideal just for a Noetherian ring. So if you have a Noetherian ring, you have two ideals I and J. Then we say J is a reduction of I if it satisfies this equality that J times I to the M is equal to I to the M plus 1 for all large values of M bigger than equal to N. So now, since this holds for all M bigger than equal to N, and this N is dependent on J, let's capture this information. So given any J, there'll be an N. So we want to capture this information as R sub J of I. This is the minimum N such that this equation holds for all M bigger than equal to N. In order to define the reduction number of an ideal, we need a notion of minimal reduction. So if a reduction J is minimal with respect to inclusion, then we call it as the minimal reduction of the ideal I. It's kind of connected to the analytic spread of I, but the information we need in this setup is because the ideals are M primary. Whenever I say J is a minimal reduction of I, it will be generated by precisely D elements where D is a dimension of the ring. And that's the only information we need as of now. So once we have a minimal reduction, we can define a reduction number. Reduction number is the minimum value of R sub J of I, where J varies over minimal reductions of the ideal I. One popular class of ideals that are studied in terms of their reduction number is the class of ideals which have reduction number 1. These ideals are called stable ideals, and they have actually very nice properties. For example, they're associated greater rings of Cohen-Macaulay. And there are various connections, there are various results in the literature. There are results by Northcott. In characteristic P, there are results by Watanabe and Nishida, where they study Hilbert-Sample functions and Hilbert-Sample coefficients of ideals which are stable ideals. So this is some idea about the reduction number of an ideal. So how do we use all of this setup, and what do we prove? So let's get back to one. So this is a result from my paper with Mr. Kole and Jacob Wagner. And this is. So we started with one-dimensional rings, and we wanted to compute the Hilbert-Kunz multiplicities. And the setup again was R is Noetherian, local. As I said, we want P to be 1, the dimension of the ring. And of course, we are in characteristic P. And now we are considering I and J. These are M-friendly ideals. And in this setup, we want to look at the Hilbert-Kunz multiplicity of the ideal J, comma IP in the Rees algebra of the ideal I. And we actually prove that, surprisingly, this is only dependent on the Hilbert-Simon multiplicity of the ideal J. Nothing else appears. I would quickly like to give a proof of this. And I guess I can, yeah, I can do that. Okay. So this will be just like a nice sketch of the proof. It requires like small things of characteristic P reductions, integral closure, which I'm unable to resist. Okay, so how do we prove that the Hilbert-Kunz multiplicity of such an ideal in the Ries algebra is equal to the Hilbert-Simon multiplicity of the ideal? So first of all, we try to reduce the setup to something we have a better hold on. So my first claim is, of course, before that, since I'll be using reductions, we may assume that residue field is infinite. This one can do by passing two general extensions. And once we have residue field to be infinite, it guarantees that we have minimal reductions. And as I mentioned, minimal reductions are generated by the number of elements. In particular, if I'm looking at a minimal reduction of ideal I and J, then they will be precisely generated by just one single element because we're in dimension 1. So what is the nice setup that I want to reduce it to? I want to claim here that in order to compute the Hilbert-Kunz multiplicity of J comma IE and such of I just want to compute the Hilbert-Kunz multiplicity of X comma YT and R of I, where X in I and oops, that's X in J and Y inside IP. This is okay, let's do this in the ring R and not pass with the research. So Y is inside I. These are minimal reductions. So what we did was for every ideal J and I, we picked up their minimal reductions, X and Y respectively. We looked at the ideal X comma YT in the Ries algebra of I, and then we claimed that these two Hilbert-Kunz multiplicities are same. And of course, it is, in order to prove the claim, it is sufficient to show that when I look at the tight closure of these ideals, they match. Once that is true, we'll be done, at least with the claim. So it is sufficient to show that when we are looking at the tight closure of J comma IP, this is same as tight closure of X comma YT. And there's actually a nice quick way to see that. Okay, let's start by looking at the tight closure of X in the Ries algebra. So this actually comes from a corollary to Bryan-Skoda theorem. A quick corollary of this result says that if you have an ideal which is principally generated, then its tight closure is actually equal to its integral closure. But now what happens over here is the following. X is a minimal reduction of the ideal J, and it will continue to be a minimal reduction of the ideal J in the Ries algebra. So this means that integral closures will continue to be the same in the Ries algebra. But now the integral closure contains the tight closure of the ideal, and also since X is contained in J, the tight closure of X in Ri will also be contained in the tight closure of J in Ri. And if you look at these two equations, this will say that tight closure of X in Ri is actually equal to tight closure of J in the Ries. And similarly, of course, we'll have that if you look at YT in RFI, its tight closure will be same as the tight closure of ideal IT in the research. Once we have this, now we use a quick property of how does the tight closure behave when we are looking at sum of two ideals? And that's how it looks. So if we are looking at x comma y t, it's tight closure. This is same as taking the individual tight closures of these ideals. And now we take the full tight closure of the sum of these two ideals. That's how the tight closure behaves when we are taking sum of two ideals. And now we know precisely what to do with the right hand side. This is GRI star plus ITRI star. But again, using this definition of, using this property of tight closure again, this is GIT, RI, and it's tight closure. So these two ideals have same tight closure, and they have same Hilbert-Kunz multiplicities, and this means claim holds. This means we only need to bother about the Hilbert-Kunz multiplicity of the ideal x comma yt in the Riesz algebra of I. But now we are in a nice setup. The ring was one-dimensional. This means the Riesz algebra is two-dimensional. We have ideal generated by x comma yt, which actually forms a system of parameters. And for a system of parameters, Hilbert-Kunz multiplicities coincide with their Hilbert-Samuel multiplicities. That's x comma yt in Ri. But as I said, there are minimal reductions of ideal J and IT. This means their Hilbert-Samuel multiplicities will again coincide with the Hilbert-Samuel multiplicity of the ideal J comma IT. And now we kind of use a result from Professor Jugal paper. And I guess this is back in 1988. We proved that in this setup, the Hilbert-Samuel multiplicity of the ideal J comma IT is just the Hilbert-Samuel multiplicity of the ideal J, and nothing else appears. And that is what finishes the proof. So it requires like many small things, but that's how it ends up proving that we have this Hilbert-Kunz multiplicity of the J comma IT in the Riesz algebra, and it came out to be just totally dependent on the Hilbert-Samuel multiplicity of J. There was nothing else, and it was also independent of the ideal I we began with. So this was about Hilbert-Kunz multiplicity. Before I end my first part, I want to also say something about the Hilbert-Samuel multiplicity over here. So let's quickly look at that. So again, we have a one-dimensional ring. So P will be equal to 1, Noetherian local ring, and prime characteristic P. Over here, we have an M prime VIP, right? And we want to look at length of the ideal I comma IT square bracket Q in the Riesz algebra of I. So we are looking at the Hilbert-Kunz function of the ideal I comma IT in the Riesz algebra of I. The only restriction we have, or rather the only condition we have, is I is M prime DID. So how does this length function behave? We prove that this is quasi-polynomial for large U. Of course, we also give a proper expression of this. For time constraints, I'm not putting that expression over here, but we did see that once we look at the expression of Hilbert-Kunz function of this ideal, we saw Hilbert-Samuel multiplicity appearing. We saw E1 of the ideal I appearing, and we also saw this alternating nature, the periodic constant nature, which we saw in Monsky's result, also appearing here. And that's why we have this function to have quasi-polynomial nature for large values of T. But this is I comma IT. We thought, since we computed the Hilbert-Kunz multiplicity of J comma IT, we thought let's try to compute the Hilbert-Kunz function as well for a general ID, J comma IT and not just I comma IT. And what we could achieve was the following. Again, we have to mention one, but now the setup says that additionally we have R to be Kuhn Macaulay, and I is parameter ideal. It's generated by system of parameters. And we have an ideal J, which is n prime. Now, if we look at length of Lee's algebra over the ideal J comma IP Q, then this length is actually Q squared times multiplicity of J plus Q times alpha sub J E, where this alpha sub J of E is capturing the alternating or the periodic part of it. So alpha sub J is length of R over J squared Q minus multiplicity of J plus Q. This is periodic function of E, and of course, this is all true for large values. So that's how the situation looks in dimension 1. And let me quickly say how it looks in dimension, which is higher than 1, basically bigger than equal to 2. And with this, we'll kind of halt with the first session. But before going to dimension 2, we saw something which was a little more generalized in terms of the characteristic P setting. And this is something which is called as a generalized Hilbert-Kunz function and Hilbert-Kunz multiplicities, which were coined as a term by Konka in 1983. And I guess his idea was to look at characteristic setting. In particular, we do not want to restrict, we do not want to restrict ourselves to Frobenius powers, which are, just taking powers of primate, of the prime that we begin with. We want to just take a natural number and try to take the corresponding Frobenius power, if it makes sense. So his setup was the following. He looked at Noetherian local rings or standard graded. Respectively, M is the maximal ideal or the maximum homogeneous ideal, I is M prime D. His setup required fixing a generating set, because if we are looking at any natural number S and then raising the generators to that S power, this ideal ought to be relied on the generating set to begin with. Because once we further look at this length function, length of R over I square bracket S, this kind of is dependent on the generating set to begin with. So that's how he defined the generalized Hilbert-Kunz function. You look at any natural number S, you fix a generating set. I square bracket S is actually either generated by the S powers of the individual elements in the generating set. You look at the corresponding co-length, that's a Hilbert-Kunz function. You look at the limit, this is what is called as Hilbert-Kunz multiplicity. But the catch over here is that this limit may not exist. Of course, one can define these terms, but the limit must exist to begin with. And this was actually proved by Bookweitz and Kahn, I guess, later. They just gave an example where this limit did not exist. But there are certain cases where this limit does exist. And this paper is actually the place, a Konka's paper, where he computes all these numbers when your ring is quotient of a polynomial ring by either a bunch of monomials or a single binomial. So there are certain cases where this limit indeed exists, and this characteristic free notion of Hilbert-Kunz functions and multiplicities does make sense. So once we have this, the idea is to see if we can have this characteristic field notion in high dimensional cases. And that's what we proved. We looked at dimension D bigger than or equal to 2. We assumed R is Cohen-Macaulay. We looked at parameter ideals, and then we computed the so-called generalized Hilbert-Kunz function of I comma ID. And that's how this expression looks like. The expression, of course, indeed looks nice. A few things to notice over here. Again, we see Hilbert-Samuel multiplicity of the ideal appearing. The other part of it is only dependent on the crude dimension of the ring. And that's it. And of course, this equation holds for all S bigger than or equal to D. So we have a polynomial nature of this Hilbert-Kunz function appearing. And once you expand this term, this also says that when we look at the Hilbert-Kunz, the generalized Hilbert-Kunz multiplicity of the ideal, I comma ID in the Lee's algebra, this is actually CD times the multiplicity of the ideal I, where again, CD was the one I mentioned before. CD is 3 times 2. So before I stop, okay, I'll take a minute. I just quickly want to say what really went into the proof, because it's highly computationally intensive. but there are a few pointers that I would like to say. So how does one start thinking about computing these lengths? And what we did was the following. So since we are talking about this ideal, which is finite length, this means when we look at this quotient ring, this has only finitely many non-zero gridded components. So the idea is to find an upper bound on this gridded component beyond which we know all the gridded components are zero. Now, once you have this bound, you would want to compute all the lengths which come up in between. Next step, once you get a hold of how to compute these lengths, you would want to simplify. So how did we simplify? We used combinatorial techniques, a few of them being using Stirling numbers of first kind, Stirling numbers of second kind. But before that, we had these finitely many lengths that we had to compute. And how these lengths looked like was, it's an interesting story in itself, but I'll just quickly say the main part of it that was that was a little non-trivial. So we had this function f, which is dependent on two variables, which is length of I square bracket s, I square bracket s times a to the n. And one had to compute this length in order to proceed. And as you can see, it's like a mixed combination of ordinary powers and the so-called generalized Frobenius powers. And under the setup of the theorem, where the ring is Cohen-Macaulay is parameter ideal, we could actually precisely say how does this function look like. And whatever over here appears is actually just dependent on the dimension of the ring and the Hilbert-Samuel function. So h by hn, I mean the Hilbert-Samuel function. And this is h to the d times the multiplicity of the ideal. And this is like for various values. S plus 1 until a certain number, and then of course n below n equals a certain number. And this required, looking at associated graded rings, Koszul complexes, using properties of Cohen-Macaulay rings, and a ton of things. So of course, this was one of the length factors which came up. And there were a few more other things that came up into the calculations. So the step was to figure these out. And then of course, once you have all these numbers with you, you have to simplify and then use Stirling numbers to simplify them to make the final result look as nice as this possible expression. So this was my story about Rees algebras. I guess I'll break here for 5 minutes and then we'll pass to the second part of the talk.
Okay, thank you, Kriti. Is there anybody have any questions for Kriti now, or there'll be a chance after her talk's over also to ask?
May I ask a question? Sorry.
Yes, sir.
Yeah, so can you go to the definition of like just previously when we were proving that is a quasi-polynomial?
You want to look at the definition of quasi-polynomial?
No. Where you were proving that it is a quasi-polynomial, you had a theorem, no, which was saying it is a quasi-polynomial. Yes. Here, how do you know that alpha j of e equals that expression? L of...
Oh no, this is just my notation. When I say alpha sub g of e, this is what I meant.
Okay.
This is just a notation for this expression. The idea to do this substitution over here is because this expression comes from Monsky's result. We are still in dimension 1. And Monsky proved that if you have an expression of this kind, this is a quasi-polynomial.
So this period, the period of alpha j, does it have any importance, like the number?
I'm not sure if it is computed in many examples. So I have seen examples where period is 2. I'm not sure, but I guess there is a paper of Kunz where the very first paper, 1969, I guess there's a result where he computes the Hilbert-Kunz function and the period is 3.
I see. Okay.
But I'm not sure if many computations are done.
No, I was asking if if you know the number of generators of 5, whether that has anything to do with the period.
I don't think so, no.
Okay. And the last question is that in the top, when you defined Hilbert Samuel multiplicity,
Mhm.
and then you defined Hilbert Kunz multiplicity, but Kunz was for a specific power of ideas, Frobenius power of ideas. Do they match? Like
Hilbert
this?
Kunz multiplicities and Hilbert Samuel multiplicities?
Yes.
Oh, so in dimension one, these two notions coincide.
Mhm.
But for high dimensional cases, you just have this equality that you can actually easily prove. So if you look at Hilbert Kunz multiplicity of an ideal, then it is actually sandwiched between the Hilbert Samuel multiplicity and Hilbert Samuel multiplicity over vector.
Okay, thank you. Also, do they like behave like polynomials? You're multiplying polynomial coefficients. Do they behave in that way? If you change your I to, let's say, I cube, will this come from I1, I2, the the multiplicity of
The
I1? Yeah,
Hilbert Kunz multiplicity. This is what I'll talk about in the second part. How does Hilbert Kunz multiplicity of powers behave? Because for Hilbert Samuel multiplicities, we know what happens, but that does not happen for Hilbert Kunz multiplicities.
Oh, I see. Okay, thank you.
Proof that, in the first proof that you showed, the dimension one case, at some point you were saying that the type closure coincides with the integral closure.
Yeah.
Is that just because it's a principal ideal, or is that all?
Yes,
or
because
the required dimension one? That's the part that I'm confused about.
I suspect it requires dimension one because see, dimension one played a role in firstly when we were picking minimal reductions. Minimal reductions turned out to be principal. And for principal ideals using Branscom's-Coda theorem, I could say that integral closure coincides with the type closure.
Okay.
So like there are many steps which I'm not sure will hold up in high dimensions. It's because of this principal nature. Principal ideals, of course, are like easy to do.
Okay. And at some point you mentioned this result of Kunz in dimension one. Are you using it in this proof or not?
No, no.
Okay.
Yeah, I guess the only thing we do tend to use in whatever I showed was this result of Monsky. Yeah, over here. So this alpha sub G of E that we were just mentioning is actually this delta E. And this kind of appears at several places in dimension one scenario. So this result is extensively used.
Okay, thank you.
I have a quick question, Kriti, if I may. Is there a, let's see, when you talked about the S power, and you said that limit may not exist, is there an easy example where it doesn't exist, or is it just some complicated counterexample that?
Oh no, that's a pretty easy example.
Okay, yeah, the generalized Hilbert-Kunz function. That's it. Yeah, or the multiplicity.
Gosh, I have to recall this, but it's a very simple example where they look at quotient of polynomial ring K x y z over, I know, x plus y and x plus z, something like this. It's a pretty nice idea. And then they prove that there are two different subsequences where the limit converges to two different numbers. Yeah.
So you said divide by x plus y and x plus z?
I have to recall. I may be guessing, but okay, let me see if I can quickly pull that. Abdel, do we have a minute or so?
Yeah, I mean, I think you can answer this question, and then the other questions probably should be left to the end of the talk.
Okay, I'll try to see. Oh yeah, so this is the ring is kxyz over x plus y plus z.
X plus Y plus Z, okay.
Yes, and you're looking at the maximal ideal, and you look at two subsequences. So characteristic P is, okay, they're still saying characteristic P, but we are just bothered about taking powers which are not just Frobenius powers. They could be natural numbers.
Oh, I'm
So
sorry,
if-
so this is also for characteristic P, is that?
The example does do that, but I guess the idea over here is to look at natural Frobenius powers and not prime
Okay.
numbers. Yeah, over here
Okay.
they look at like two subsequences, which is P to the E and 2 times P to the E. So in Frobenius powers, 2 times P to the E will not make sense. But for natural Frobenius powers, it does. And for these two different subsequences, the limits are different.
Okay, thank you.
Oh, okay, are you ready to start up again, Kriti, or do you
Yeah, I'm all charged.
need to rest for a moment?
Okay, yeah, I guess we'll start. So the second part will have a different flavor in the sense that the story of free algebra is done with. Of course, I had a few more things, but I guess I'll just keep them aside. Let's look at the other part of things. Let's look at a different difficulty level. Not to brag about it, but yeah, it's a different level of difficulty in the sense that now we want to look at Hilbert-Kunz multiplicity of powers of ideals. So for Hilbert-Samuel multiplicities, we know what happens. So if I have just an ideal I, and then I'm looking at Hilbert-Samuel multiplicity of I to the k, and of course, these the dimension of the R, then this is k to the d times the Hilbert-Samuel multiplicity of the ideal I, and it's pretty easy to prove. You can just do it with the definition of the Hilbert-Samuel multiplicity. But this definitely does not happen when we look at Hilbert-Kunz multiplicities of powers of an ideal. And the motivation to look into this actually came from a paper of Elias Murner. And this was in 2019, where, of course, I'm kind of continuing the setup from before. R is an Noetherian local ring. E is the dimension of the ring. M denotes the maximal ideal. Characteristic P will be there with us. And yeah, I is an M-primary ideal. So if one looks at the Hilbert-Kunz multiplicity of I to the k, where k is a natural number, Ilya was able to prove that in this setup. So the idea over here is the following. We want to write this number as a function of k, a function of the power. And of course, our favorite way of doing this is writing this in terms of binomials. So the leading coefficient here, surprisingly, unsurprisingly, is the Hilbert-Samuel multiplicity of the ideal. We could prove how the next coefficient looks like. This is limit to tends to infinity E1 of I squared by Q over Q to the D. Oops, okay. Scalar. So k plus e minus 2 choose k minus 1, and whatever else is of order k to the minus 2. And this he could prove for all large k. So Hilbert-Kunz multiplicity of I to the k, when seen as a function of k, looks like this. And of course, again, this result of his was also inspired by a few more results from the literature, the latest being a result by Vijayalakshmi Trivedi, where she proved kind of the same result, but she had a specific setup that the ring was standard graded ring. I was a homogeneous ideal generated in same degrees. So there was a specific case where this result was proved, and Ilya was able to prove this in a lot more general setup where the ring was a Noetherian local ring. I was a M-primary ideal. So of course, now once you look at this equation and then you see Hilbert-Samuel coefficients and their asymptotic limits appearing, the natural question which one would ask, and that's what even Ilya asked in his paper, rather two questions were, the first one, is it true that when we look at the limit of other Hilbert-Samuel coefficients of the ideal, the fruitness bound of the ideal. So does this limit exist for all I bigger than or equal to 2? Of course, the second question will be, of course, so it's like does or when you may require additional conditions. So when for large K, we can write the Hilbert's multiplicity of I to the K as our favorite expression, which is the alternating summations of binomials times the asymptotic limit of I of I squared by Q to T. So under what conditions do these questions have an affirmative answer, or under what conditions they may not have? We kind of focused on finding the conditions under which they do have an affirmative answer. We still do not know under what conditions they may fail, but we are still looking into it. So let's focus on under when is this nice thing possible. So the very first result that we have is, of course, before we go further, what are some very basic assumptions under which these two questions will have an affirmative answer? And the very first which comes to mind is entering is Goel-Macaulay and is generated by a system of parameters. Under that setup, we all know that, or rather it's easy to check that when we look at the Hilbert-Samuel coefficients of I square bracket Q, because I square bracket Q will also be a parameter ideal, the Hilbert-Samuel coefficients EI of I square bracket Q will all be 0, starting with I bigger than or equal to 1. It's an easy exercise if you haven't seen. So in Goel-Macaulay ring, I generated the system of parameters, the EIs vanish, and of course, then the asymptotic limit will be 0, and this expression will also be nice. So the next best step is, what if you want to assume something which is lower than Goel-Macaulayness, and the thing we targeted was the Book's-bound property of the ring. And now this is a different paper. This is my recent paper with Anandam Banerjee and Jyoti Verma. And over here, we prove that if R, this is a Book's-bound ring, of course, T is the dimension, the full dimension of the ring R, characteristic of the ring is positive prime P, and we have I generated by system of parameters. Then what really happens is the following. We firstly want to look at the asymptotic limit of the Hilbert-Samuel coefficients. All of these, they turn out to be 0. The second, the Hilbert's multiplicity of I to the K, we are able to prove that this only is dependent on the Hilbert-Samuel multiplicity of the ideal times the phi. And this holds for all K. So that's one nice result, one promising result in the sense that there are other conditions under which these two questions have affirmative answer, and there's a hope possibly that we can look more further. So let's look further. So next result, what are the extra assumptions under which these two things are true? And in the next result, what we actually prove that if we have the usual setup, but over here, oh, okay. If we have R to be Goel-Macaulay, of course, T is a dimension, P is prime characteristic, I is M prime now. And we have now the extra assumption that we put is on the depth of the associated graded ring of I square bracket Q. If this depth is at least P minus 1 for all large Q, then we can say these two questions have affirmative answers. And not just that, we can actually give an expression of how the asymptotic limits look like and what is the exact expression of the Hilbert's multiplicity of the powers. The extra assumption being that the ring is Cohen-Macaulay, and when we are looking at depth of associated graded rings of the Frobenius powers of the ideal, they are at least D minus 1 for all large values of Q. Yeah, so let's look at the expressions first. So if this is true, then first of all, if you're looking at the asymptotic limit, then let's give it Q. This is this one. Oops. So this expression is kind of dependent on the reduction number of the ID. The I, this indexing factor goes from 1 up to the reduction number times this binomial. What we expect inside is the Hilbert-Sandel multiplicities minus summation J dimension, alternating sum, we choose J. And what so unsurprisingly comes are the lower values of Hilbert-Kunz multiplicities of powers of I. That's how it looks like. So once you have these assumptions, and once you know what the reduction number of an ideal is, it's computable in the sense that you only have to look for Hilbert-Kunz multiplicities of these lower powers. And once you have this expression, one would want to know how does the Hilbert-Kunz multiplicity looks like. So let's quickly look at that as well. So this is as expected, but now for all n, we're going to make R minus T plus 1. So R is the reduction number, T is the dimension of the ring. In this case, if you look at the Hilbert-Kunz multiplicity of n, okay, I should have said key. So, of course, like what we would expect. Like the expected behavior, but this expected behavior comes beyond this number, which is reduction number minus the dimension. That's right. So we do have the expected expression. We do know what the asymptotic limits look like. And just to quickly motivate you that indeed this expression is something which is valuable in the sense that using only finitely many numbers, we can get information about Hilbert-Kunz multiplicity of really all the powers, or rather most of the powers of an ideal. I would quickly give an example. So the ring that we want to look at over here is characteristic 3. It's a quotient of power series ring in 3 variables by x cubed minus y cubed z. So that's the ring I'm looking at. M, of course, is the maximum homogeneous ideal x, y, z. And we want to compute the Hilbert-Kunz multiplicity of powers of this maximal ideal. So we have a few things to check. Of course, this ring is Cohen-Macaulay to begin with. So that's one tick. The other thing we want to check is looking at the associated graded ring of the Frobenius powers of the maximal ideal. In this case, it requires a little bit of checking, but we do have that this is Cohen-Macaulay for all values of Q. It's a quick check. I don't want to delve into it, but that's what happens. Okay, just to be on the safe side, let me just say it's for large. Yeah, let's keep it for large values of Q. We know it's Cohen-Macaulay. And now, since all the base assumptions are satisfied, we want to look at what is the reduction number of maximal ideal. Once we have this, we can plug everything in formula number 1. So that's one thing. The other thing is when you look at the ideal y comma z, this is minimum reduction. And reduction number of maximal ideal is equal to 2. That's a bit easy to check. But once we substitute everything in 1 and 2, that's the final formula we get. We get Hilbert-Kunz multiplicity of n to the k. It's Samuel multiplicity times 2 minus 2k plus 1. K minus 2 times the Hilbert-Kunz multiplicity of the maximum ideal plus k minus 1 times Hilbert-Kunz multiplicity of m squared. That's it. And this holds for all k bigger than or equal to 3. And if you look at the expression, there are only 3 things to compute. Hilbert-Samuel multiplicity of the ideal, Hilbert-Kunz multiplicity of the maximal ideal, and Hilbert-Kunz multiplicity of n squared. Once you have just 3 numbers, you know precisely how does the Hilbert-Kunz multiplicity of all the higher powers of maximal ideal look like. And what is this number? So let's quickly see if we can compute these 3 numbers and then we'll be done. So first of all, what is Hilbert-Samuel multiplicity of maximal ideal? This is 3, because we are looking at a hypersurface where the initial form is 3. Requires a bit of knowledge of Hilbert-Samuel multiplicities, but that's how it looks like. Next thing, Hilbert-Kunz multiplicity of maximal ideal. So in the beginning, I mentioned about, like somewhere in the talk, I mentioned about this paper of Konka, where he was computing the generalized Hilbert-Kunz multiplicity of portions of polynomial rings by a single binomial. And this binomial does fit into his setup. And if you plug in into the formula that he provides in his paper, you get this as 3. So this comes from Konka's paper. Now, the only thing remaining is Hilbert-Kunz multiplicity of m squared. In order to compute this, one has to look at length of r. Of course, since we are looking at the length function, we can as well pass to the polynomial ring instead of the basis. So one has to look at x, y, z, or of course this will be x cubed minus 5 z. This plus m square bracket cube. This is the length computation that we have to look at. So we do 2 things. We try to find the Grobner basis. Once we have the Grobner basis, we would want to look at the initial angle generated by that Grobner basis, and this length will coincide with that. So 2 steps: taking Grobner basis and looking at the initial angle. And once you do that, this length is seen as length of k x, y, z over q y to q y q z q and z to q. And this in this case turns out to be 9q squared. In particular, when we look at the Hilbert-Kunz multiplicity of n squared, this is 9. So we know precisely what these numbers are. We know what is E0 of m. We know what is EHK of m. We know what is EHK of n squared. Plug it into the formula, and now, voila, we have the formula for Hilbert-Kunz multiplicity of m to the k for all k greater than or equal to 3. And that's what this theorem does. Okay. So now once we have this, of course, there are a ton of examples where this depth condition on the associated graded ring of Frobenius powers of 5, this is satisfied. We give a bunch of examples. I'll actually give a class of rings where this is true. This is what I'll talk about next. But there are also some cases where this is not true. There are some cases, or rather, there will be questions about under what conditions is this depth condition satisfied. We're still thinking about it, but if you have any ideas on that, I would like to know, and we can discuss about it. But it'll be an interesting question to see under what condition is this assumption true. So, yeah. Okay. So these are the main two results that we proved. But again, we were trying to look for a class of rings where one could compute these Hilbert-Kunz multiplicities of powers without many assumptions to begin with. And of course, we want to look at a broader class of rings and ideals where one could do this computation. And the class of rings that we picked were Steinhausen rings, or phase rings of simplicial complexes. So this is what we'll talk about next. Again, the computation we do over here is a generalized Hilbert-Kunz function and a generalized Hilbert-Kunz multiplicity computation that will happen. So this is, okay, I'm not writing here, but yeah, this is kind of a generalized sense. We may be characteristic free in here. So the setup over here is as follows. So R is K delta. For that, same thing. Delta is a simplicial complex. Dimension is P minus 1. So if you're looking at K delta, which is the corresponding standardness in the ring, then dimension of R will be D. How will it look like? This will be a quotient of polynomial ring. Let's say we had R variables to start with or R vertices to start with. Then this is quotient by a square free monomial ideal I delta. This is square free monomial ideal. And this is exactly one of the main properties of this ring that we use over here. Since it's a square free monomial ideal, we exploit this fact that I delta can be written as intersection of primes P alpha, where P alpha are subsets. They're generated by other subsets of the variables that we began. This is actually one of the important factors which goes into the technical part of it. So now once we have this, we want to look at a class of ideals where we can compute the Hilbert-Kunz multiplicity of their powers. And the ideals over here that we want to look at inside R are the ones generated by pure powers of the variables. So we want the cycle to be imprimary. This means all the VIs have to be strictly bigger than V. So that's the setup we have. So this is the ideal generated by pure powers of the variables. Each of the power has to appear. Is there a question? Okay. And we want to compute what is the Hilbert-Kunz multiplicity of J to the K in the standardized ring. And this is what we prove. So this is the same paper with Addington and rest of Redmond, where we prove that in this above setup, two things happen. First of all, when we look at the asymptotic limits, these are all 0 for all I equal to 1. And secondly, this will say that if you look at the Hilbert-Kunz multiplicity of J to the K, oops, this was a J here. Then this is only dependent on the Hilbert-Sample multiplicity of J plus 1. And this is true for all K bigger than equal to 1. So that's how this expression looks like. But when we looked at the class of these standardizer rings, there was actually one more reason to look into it. And in the last 5 minutes, I guess I'll just talk about that. So apart from the questions that India proposed in his paper, there was also a conjecture. A conjecture which is kind of motivated from various results in the literature. So in the beginning, when I talked about Hilbert-Sample functions, Hilbert-Sample coefficients which appeared in the polynomial, okay, I don't recall if I explicitly said that, but one reason why these functions and polynomials are extensively studied is because using these coefficients, the Hilbert-Sample coefficients, people in the past have characterized various properties of the ring. Like, of course, Hilbert-Sample multiplicities can help characterize regular rings, but there have been results where people have used even of I to characterize certain properties and so on. Of course, even E2 also comes up in a few results. So in this characteristic P setup, and since we have this asymptotic limit of EI of I square bracket Q appearing, is it possible that one can characterize properties of rings using whatever we have now? And I guess this was the motivation of the conjecture. And that's what he proposed. The conjecture says that if R is a Cohen-Macaulay, of course, a Noetherian ring, then Of course, I is n primary, not to forget that. Is it true that I is stable ideal? So what was a stable ideal? It is an ideal, the reduction number is 1. Is this true that an ideal is stable, it has reduction number 1, if and only if, when we look at the difference of Hilbert-Samuel and Hilbert's multiplicity of I, this is precisely the asymptotic limit of E1 of Q. That's the question. Or rather, that was a conjecture that I is a stable ideal if and only if the equality on the right hand side is true. And when we looked at the class of Stanley-Reisner rings, okay. So what does it say over here when we look at the second statement? If K is equal to 1, this implies that Hilbert's multiplicity of J, this is actually equal to the Hilbert-Samuel multiplicity of J. And now let's come back to the conjecture here. So if R is a Stanley-Reisner ring, I is the ideal we saw generated by pure powers of variables. Then let's look at what happens to the right hand side. The Hilbert-Samuel multiplicity coincides with the Hilbert-Kunz multiplicity. So this means this will be 0 equal to, but now using part 1, we also saw that the asymptotic limits of these EIs is 0. In particular, this is 0 equal to 0. In particular, right hand side is always true, irrespective of the reduction number of the ideal I we began with. So this means conjecture does not hold for the case of Stanley-Reisner rings. When ideal is generated by pure powers of variables, we even did not require it to be Cohen-Macaulay. So it was just like class of Stanley-Reisner rings. So of course, then this means we have to revise the conjecture. This means you have to look for further examples, further extra assumptions under which this may be true. And now that's an open ground. What kind of assumptions do you want to put? You want to put assumptions on the ring, on the ideal. What is it that can make, or do you want to, modify the statement, add something on, over here or over here? That's of course one thing that people can think about. We are also thinking about it, but the difficulty level in this computation is computing these asymptotic limits, because you have to do this for all large values of Q. You have to look at Frobenius powers, and in order to compute E1 of I square bracket Q, one has to actually look at mixed powers in the sense that one has to look at length of R over I square bracket Q n. Now this length can be seen as Hilbert-Samuel function of I square bracket Q, or it can also be seen as Hilbert-Kunz function of I to the n, because ordinary power will come with the Frobenius power. But again, these two things, these two computations pose their own challenges. So under what conditions you can do this computation, figure out how does this asymptotic limit look like? Or are there other techniques? Because this is just like going by brute force. But are there other techniques using which can you compute this, look at a class of examples, revise the conjecture, and say something better? So yeah, I guess with this, I guess I can stop over here. That was the idea of the second paper I talked about with Banerjee and Verma. That's a recent paper in 2022, where we look at Hilbert's multiplicities of powers. We start with giving certain assumptions under which the asymptotic limits of the Frobenius powers, the Hilbert-Samuel coefficients of Frobenius powers, they exist. As a consequence, we get the formulas for Hilbert's multiplicities of powers of ideals. Next, we try to target a conjecture, which was proposed in the same paper of Elia. We proved that in the case of Stanley-Reisner rings, this conjecture fails. Yeah, so that's it. And I guess with this, I'll wind up my talk and I'm open for questions. And any ideas if you may have, I'll be open to that as well. Thank you.
Thank you, Kriti. Are there any questions? Mhm.
I do have one question.
Yeah.
So there was this theorem where you have this assumption on the depth of the associated greater ring of the powers.
Yes.
I don't know how technical that is, but can you say a bit about how that assumption is used in
Okay. Oops, why can I not find it? Yeah. It's a little technical in the sense that the basis of this assumption actually comes from a result of Tom Arley in his thesis, where if we have a Cohen-Macaulay ring and then we have a bound on the depth of associated greater ring of the ideal, we get certain bounds on the reduction number of an ideal and something which is called as the postulation number of an ideal. So postulation number is beyond the number where the Hilbert-Simon polynomial coincides with the Hilbert-Simon function.
I see.
So, and we need those bounds to get some computations going on, because that's why you see this reduction number also appearing over here.
I see. And I guess that's where you need the ring to be Cohen-Macaulay, right?
Yes. Yeah. So both these assumptions of Cohen-Macaulay and the depth, they actually come from a result of Tom.
I see. And I have a seemingly related question. In the theorem that is right above this one, you have a Buchsbaum assumption.
Yes.
Where is that used?
Okay. Buchsbaum actually, with this assumption, I guess there's a paper of Chung where he computes these Hilbert-Simon coefficients somewhere. It's not very direct. But the main idea we use over here is that whatever expression from his paper that we can get of Hilbert-Simon coefficients it's independent of the value Q over here.
I see.
Like he gives some expression in terms of local cohomology modules, but the idea is it's independent of the Frobenius power that is coming up. That's why when you take the asymptotic limit, it turns out. So.
I see. Okay. Thank you.
Are there other questions? Well, if not, then let's thank Kriti again. Thank you.
Thank you. Thank you for the invitation once again.
So, Carl, you're the technical manager.
Yep. I'm going to stop recording.